Alright, still in the middle of 4-4 here. Welcome to part 3. Alright, using the diagram in example 1, write a two-column proof. Oh, wait, so that's not this diagram. Just like, well, that took a while, but I finally got the diagram up there, or the diagram from example 1. Okay, given that AD is congruent to CD, and that measure of DAB, that whole thing, is congruent to DCB, so it looks kind of like the converse of what we're talking about before. Prove that AB is congruent to CB. I really want to draw an auxiliary figure here, but it wouldn't help. You want to see what I mean? I want to draw in DB and call it a shared side, and then I'd have maybe I can get some triangles congruent, but it would be side-side angle, so it's not going to help. So let's try a different tactic. Yeah, I can see an annoying little tactic that's going to be basically the same as what they did in the example above, but we would do sort of the converse. In that, yeah, I got the given stuff. Yeah. Given stuff is down there. From that, I have angle 1 is congruent to angle 3. Remember, this is all about isosceles triangles before. I have an isosceles triangle ADC with AD equal DC. So ITBAT or ITT angles tells me 1's congruent to 3. Well, I could subtract. Now, remember, I had this angle congruent to this. I could subtract those off. I could say the measure of angle DAB minus angle 1 equals DCB minus angle 2 because of the annoying angle addition. Oh no, I'm sorry, I'm not doing that yet. All I'm doing, I'm not saying what that angle is. I'm just saying I can do this algebraically. This is subtraction probability of equality. Then angle addition can tell me what that actually is. DAB minus 1, well that's, oh, can you see this over here, step 4. DAB minus 1, that's really angle 2. And DCB minus, that's a C. DCB minus 2, that's really angle 3. And that's angle addition of postulate. So really now I'm able to say that angle 2 is congruent to angle, what? Not 3. Sorry, it's angle 4. That's really angle 4. So, whoa, how come things are jumping around on me? Angle 2 and angle 4 are congruent. Well, now if 2 is congruent to 4, then I have a little isosceles triangle down there, ABC. Namely, AB is congruent to ABC. And that's what I was trying to prove. And that is the reverse of this. That's because if two angles are congruent, then the sides are congruent. I'd call that the ITBAT converse. Somebody else might call that ITT sides. Whoa, that was scary. Okay, great. All right, example 2. This little diagram. I'm supposed to prove it down here below. Great. AB is congruent. Okay, this whole thing is congruent to this whole thing. B is congruent to angle 2. Well, that's interesting. And C is congruent to angle 1. Okay. That's given. They split this apart, which I don't like. AB is congruent to AC. That's given. B is congruent to C. Oh, how? It's not marked. How come B is congruent to C? Well, that has to do with this. Came right out of this. AB is congruent to AC. That is because it's an isosceles triangle. I get the angles congruent. So it turns out that the one arc set is actually equal to the two arc set. Those are the same. So we could say this here, basically. Angle B and angle C and angle 1 and angle 2 are all congruent. So really, I'll just call this a one arc now and a one arc. They're all the same, really. So why is AD congruent to AE? Well, now ADE is a little isosceles triangle. I knew about the angles first, so I'd call this ITT sides, or ITBAT converse. And then which one's isosceles triangle? Well, there's two isosceles triangles. The one I care about is ADE. That's the one they asked me to prove. Okay. Did I go too far there? Yeah. Using diagram example 2. Oh, okay. Using that same diagram, oh gosh, I can't see it. If AB is congruent to AC and 1 is congruent to C, so let's erase this stuff for a second. AB is congruent to AC and 1 is congruent to C. Y is probably B is congruent to, oh no, DE, why are DE and BC parallel? Oh, that's cool. Let's shrink this size so I can see it all at the same time here. Getting smaller. Okay. Can I get all this on the same page here? Yeah, okay, so I'm working on number 4 now. I erased the markings for 3. I don't think that's going to be a huge problem. If you want them back, you could rewind. AB is congruent to AC, so this big thing is still given. Great. 1 is congruent to C. Well, 1 is congruent. C is also congruent to B. Let's say that first. So this is given. Great. Save some time here. B is congruent to angle C because of that. So this is like what, step 2 now? Step 3 is, well, if B is congruent to C and C is congruent to 1, then B is really congruent to 1. I have to list that because I care about B being congruent to 1 listed because those are corresponding angles. Corresponding angle being congruent gets me where I want to go. It tells me that these are parallel. Well, that was fun. Okay, not a very common type of proof for this chapter. Okay, let's get back up to the Let's get back up to the sides I was at. Okay, all the statements and reasons for the following proofs have been provided. Oh yeah, this is the put them in order thing. Okay, if BC is congruent to DC and BF is congruent to DE, that would be step 1. And I'm trying to prove this thing, so that would be the last step. Oh, look, it's corresponding parts. That has to come after this, and this is probably somewhere in the middle. BC and DC look like that, and BF and DE look like that. BC and DC, that means this whole great big thing is one giant isosceles triangle with these two angles as part of the isosceles triangle. That's ITBAT. Book calls it isosceles triangle theorem, which is not a great name, so I call it ITBAT. It's the same thing. Or ITT angles. Great, so now it looks like we have side angle side that would tell us this. And then after that, of course, we have corresponding parts that tell us that 1 is congruent to 2. Great. Okay, I did that forwards more than I usually do. Okay, bisector the vertex angle and isosceles triangle is perpendicular to the base. But yeah, this is a proof of a theorem that's in the book. If you bisect the angle at the top of at the vertex of an isosceles triangle, it's going to be the perpendicular bisector down here. Why don't we just do that in one step and call it a day? Well, they want you to actually prove the theorem, so they don't let you use the silver bullet for this, otherwise it would be too easy. Given that AB is congruent to AC, given that's around here, great, and AD bisects. Well, you know what? I would call this step 1 also. They did it in 2 separate ones. I would call this 2. I'm sure that's not what they mean, but I like all my givens in the beginning, so that's just me. If AD bisects BAC, what does that really mean? AD bisects this angle here. It means these two are congruent. Let's just get this out of the way. Angle 1 is congruent to angle 2 because it's a bisector. Remember, this is how you say because it's in proof language. Okay. If AB is congruent to BC, I can now say right away that angle B is congruent to angle C because of the ITBAT straight ahead version, which is what they call it in the book. That's fine. Okay, and do I have enough for this ASA business? Triangle here, triangle here. Yep, they're already congruent now by ASA, so let's go ahead and say that because CPCT here is going to give me a lot of stuff. Namely, it doesn't tell me about perpendicular, but it tells me that BD is congruent to CD, and it tells me angle 3 is congruent to angle 4. Great, those are all CPCTC things. And then there's only one thing left, and it's what we're trying to prove, and it's that annoying step that if two angles are supplementary and adjacent, then they must be perpendicular. Great. All right, finally, we're into 4.5. This is HL and SS. HL and what was the other one? Oh, AAS, yeah. Okay, so we did these in my class, so I think my class has been over these enough. But maybe not everybody. State which congruent methods can be used. That means we're talking about congruence for triangles. That means we're talking these. This is all these are good for. And you have to have one of these for triangle congruence. One of the magic 5. Okay, parallels here give me AIAs wherever I want them. So right there, I've got angle, side, angle. There's nothing wrong with this, though. I could have done that kind of thing and got angle, angle, side. So those are pretty much equivalent. Actually, these two are really interchangeable most of the time. Sometimes one of them is easier to access, and really AAS is just a shortcut for ASA, but you could argue most of our theorems are just shortcut for other theorems anyway. So, but these are really closely stuck together. Here, you kind of have to go reflexive on that, and then we get SAS. The confusing thing about number 2 here is that you see this right angle, and you immediately start thinking HL. Because HL is only good for right triangles. That's true, but that doesn't mean that every time you have a right triangle that it has to be HL. All these other things also refer to right triangles too. So a right triangle could be any one of these, but this is the one that can only be right triangles, so that's why people get sucked into that one. But this is really side angle side. I don't know if the hypotenuses are congruent at the beginning. I just know this leg and this other leg. This one's got a whole bunch of reasons. First of all, side angle side is pretty easy to tell, but I didn't even use the parallels here. The parallels give me that and that, which would have just as easily been, now forget about this side here, that would have been angle angle side. And of course, that's pretty close to angle side angle, but that would require the third angle congruence, which is kind of silly. So I would kind of think those are pretty equivalent. They're pretty much one step and then this. But the steps are very different. One's reflexive and one's AAS. A good compare and contrast question on the test. Here, that's the only way to go on that. Again, I could do third angle congruence and call it angle side angle, but why? I've got AAS ready to go. Here, side angle side's ready to go. You could go reflexive here and go side, 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 or HL. I don't know. They're not that great. Really, after SSS or SAS is really the best one, and then you'd have to, because it doesn't require any extra steps. This one requires that reflexive, but again, any way you do it's fine. This one, there's only one way to do that one. This one, again, I have some stuff in the middle. Oh, now look, I've only got. People are looking at this going, oh, side side angle. Side side angle isn't one of them, but side side angle does work if it's a right triangle, and we call it HL. This one, all I've got is angles. I've got all three of them. Not good enough, so this is none. You have to have at least one side for any of those. Otherwise, you may have what we call similar triangles that are the same shape, but not the same size. So at least one length is always required. Name a pair of overlapping triangles. Oh yeah, this stuff. State which congruence method can be used for those. It says overlapping congruent triangles. So in this one, I'm not going to say XMW and YMZ because those aren't overlapping. I need stuff like XZA. Like this one kind of here. You see these kind of things a lot. And the other one might be, okay, if it's X to Z to A, it'd have to be Y. Z in one triangle would be W in the other triangle, and A is the same. All right, so for number 9, Y is XZA. From what we're given, Y is XZA congruent to YW. Well, in that one, I knew that XZ was congruent to YW. I got angle A congruent to itself. I also have X and Z. So in each triangle, which is hard to see, like if I'm just looking at XZA here, I've got an angle and a side, and that side is not between the two angles. That is angle side. Yes, there are a lot of questions like this on the test. Okay. The other thing I might do then is just change color for number 10, so you can see that on there. In 10, I think it's going to be the same triangles, because those are the only overlapping congruent triangles I see. But it's probably going to be a different reason based on what I'm given. All right, so in this one, I know, I guess, again, I got those congruent, but here I have XA congruent to YA. This is congruent to itself again. Wow, that's hard to see. Now, if you could just look in blue, I have angles at X and A, the side connecting X and A. That is going to be angle side angle. It's not a bad idea in either one of these to go ahead and draw these separately. You've seen us do this a lot now, I think. That would be the sort of the upper one, and the lower one kind of looks like this, Y, A, W. And then you can go, oh yeah, those were shared. Don't forget about that. And then mark off the stuff with the tick marks so you can really see angle side angle or side angle side better. Especially when there's two problems on the same diagram, that's really a mess. So sorry about that. 11, AB. Okay, this stuff's perpendicular. It really does look like we're talking about triangle ABC, because it said overlapping congruent. There's really only one set of overlapping congruent here, DCB. Okay. The perpendiculars I can take to the bank, but in this one I also know that AB is congruent to DC. Of course, that's congruent to itself. This really looks like side angle side. For number 12, I think it's got to be the same set. Almost out of time here. Almost snuck up on me there. This one, it's AC and BD, so I don't have the red stuff, although I do have this again. I have a hypotenuse and I have a leg in this right triangle, so that's all that is. Do I have time for this last one? Let me pause and draw. Actually, I don't really need to pause and draw anything. What's weird about this one is I could be talking about TUS and SRT, or I could be talking about TRU, and I'm not going to get that in time. TRU and SUR. So we will come back and start there in the next video.